Our next talk is on drought-resistant soil, a bound analysis. So please welcome Mitch Hunter. He's a PhD candidate in agronomy from Penn State.
Thanks a lot for the introduction. Good morning, everybody. My name is Mitch Hunter. As Sharma said, I'm a PhD candidate in agronomy at Penn State. And today I'll be talking about drought-resistant soils. And I've titled this talk a bounds analysis because I'm really trying to get at the big picture question of, can soil improvement be a tool for drought resistance that can actually affect farmers' yields and big picture drought adaptation? So I just want to start by acknowledging my co-authors, my advisor, Dave Mortensen, Dr. Armin Kamanian, who created the cycles model that I used in this analysis, as well as Dr. Charlie White. And some very brief background. We all know that drought is currently already a major yield limiting factor for crop production. And the projections are that drought will become more frequent and more severe under climate change across a pretty wide spatial extent. So this is something that we need to figure out how to address. One of the ways it's been proposed to address drought is with cover cropping and other soil building practices. And there have been a wide range of reports talking about the potential for using cover crops to adapt to drought. For instance, the 2012-2013 cover crop survey from SARE reported that for the farmers in the droughtiest states that year, they saw about a 10 to 15% increase in their corn and soybean yields in the cover crop fields versus the non-cover crop fields. That's anecdotal evidence, but it suggests maybe there's something there. So I wanted to look in and see how big can this effect be. So first, what would be the mechanisms that would be behind this? And the two that I've focused on are infiltration and storage. So from infiltration, just one example, a recent meta-analysis by Andrea Beisch showed that various alternative soil management practices, including cover crops, can lead to a pretty significant increase in infiltration rate. And for storage, this more classic paper from Hudson, 1994, illustrated that both field capacity and wilting point are responsive to organic matter, and in total it adds up to quite a bit of an increase in plant available water. So my question is, we have this kind of empirical and theoretical basis. What does this really mean for actual adaptation? And so my questions that I want to address today are, for the achievable changes in infiltration rate, how much is that going to affect crop drought stress? So I want to look at infiltration kind of on its own, and then also the same thing for soil water holding capacity. The achievable changes in water holding capacity on their own, what are the implications of that? And then finally, I want to put them together and think about the synergistic effects of the two. This, just a little bit of background, this is for me building on a field study where I did this work with cover crops. In the cover cropping project, I put rainout shelters out in the corn, and I was able to see a lot of the short-term dynamics from nutrient cycling that was occurring because of the cover crops, but in a 3-year field study, you aren't going to see the types of changes in infiltration rate and organic matter that you would need to be able to really understand this effect. So to go beyond that, I've used the cropping system modeling approach, and I've really attacked this as a bounds analysis, like I said. So I want to compare a degraded condition with an improved condition or an upgraded condition to see what is the kind of the magnitude, the quantitative scope of what we can do with this kind of change in our soils. The way I've approached this in the modeling is I've created 3 different scenarios. So first, I have the degrading scenario, which is a continuous maize system with stover removal and full tillage. Second, I have a stabilization scenario, which is a 3-year maize, soybean, wheat rotation with mineral fertilizer and conservation tillage. And then finally, an upgrading scenario, which is a 6-year maize, rye cover crop, soy, wheat, and then 3 years of alfalfa rotation. Almost everything is no-till planted in the model for this scenario, except that the alfalfa stand is plowed down with manure prior to maize planting, so that's yet another carbon addition in the rotation. A little bit of background on the cycles model. Cycles is a process-based numerical agroecosystem model. It shares modules with CropSys, in case you're familiar with that model. And it simulates crop growth processes both above and below ground in response to weather and management. It does this in the context of a layered soil. In each of those soil layers, soil organic matter responds to carbon inputs, management, and soil clay content. infiltration in the soil in this model is determined by the NRCS curve number system. And I'll go into a little bit later how that works and what that means. I do want to note that that's responsive to saturation, so a soil that's already saturated with water will produce runoff sooner than a drier soil that has more capacity to take that water in. Storage in this model is determined by the hydraulic properties of the soil. So porosity determines the maximum water storage capacity, and then field capacity and wilting point give us our plant available water. And these properties in turn are determined by the petatransfer function that underlies the model. And the function being used primarily is the Saxton and Rawls 2006 equation, which calculates these properties based on both soil textural class and soil organic matter. Now, of course, for this analysis, the petatransfer function is really critical because I'm looking at the relationship between these soil properties and the hydraulic properties. And so I started off with this analysis, and I was originally running tests based on the Saxton and Rawls equation. And what I found out was that there's very little responsiveness in that equation. So that's represented here by the gray bar. And as you can see across a wide range of soil organic matter in a silt-loam soil, there's very, very little change in plant available water. So not surprisingly, there was no quantitative effect on ultimate crop yields or drought resistance based on the Saxton and Rawls equation. However, I knew that there was in the literature some evidence of this responsiveness. So I went to the literature and I found an alternative petatransfer function from Hudson 1994 that does show a very robust response. And so all of my results that I'll be showing later on down this presentation represent the Hudson response, and I want to characterize that as probably a top bound. So in my informal review of various petatransfer functions, the responsiveness seen in the Hudson equation is probably on the high end. So there are many others, and they tend to fall in between the two. So again, thinking about a bounds analysis, how much might this matter? That Hudson equation is going to give us kind of the top bound. The modeling approach I took was to select the Lancaster County silt-loam soil, a real soil out of the NRCS Surgo database, parameterized crop descriptions for Lancaster County conditions, and then I ran my degrading, stabilization, and aggrading scenarios until soil organic matter stabilized. I then took the outputs from those setup runs, the soil organic matter distribution with depth, and I parameterized new soils that represent a degraded, stabilized, and aggraded condition. So it's mostly, the main change is that the soil organic matter distribution is different and in response to the different management scenarios. They also have different curve numbers, and I set this based on the management that was done in those setup runs. So just to give you a sense, this is the chart that you can use to calculate a curve number based on the NRCS system. I'm not going to go through it in detail. The results of this calculations show that in the degrading scenario, you'd have a curve number of 88 with a bare fallow condition outside of the cropping period. In the stabilized scenario, the curve number would be 78, a higher level of surface surface management. And in the aggrading scenario, by coincidence, it would be 68 as a weighted average across the rotation. So those are the curve numbers that are used. And to give you a sense of what that really means, here's the chart that relates for the curve number rainfall to runoff. So rainfall is on the x-axis, runoff is on the y, and you can see that for a high curve number of 88 that we have in the degrading scenario, you start to get runoff with only about 1 centimeter of precipitation. So runoff occurs really rapidly, and those curves on the left side of the chart are pretty steep, so you get runoff, it happens quickly, and pretty soon all of the rainfall is running off. In contrast, when you have a lower curve number of 68, you end up with not getting any runoff until about 3 centimeters of precipitation, and then the runoff curve is much shallower, so you're going to have a lower amount of runoff as that precipitation event continues. So you can see there's a pretty substantial difference in terms of how much water gets in the soil. The test runs that I did once I set up these soils was just annual maize production. So I'm thinking about this as like a phytometer in silico, or a virtual phytometer that tells me what's going on in those soils. And these are 36 essentially independent weather runs based on weather data from 1980 to 2015. And for all of these test scenarios, automatic nitrogen is turned on, which means that the yield differences among the years are mostly driven by weather instead of by nitrogen stress. Now for some results. First, the impact of my setup scenarios, and the impact was quite substantial. It drove about a 3% difference in soil organic matter in those surface layers between the degraded and the aggraded soils, as well as more minor differences at deeper depths. And these differences added up to 6.4% higher plant available water in the aggraded than in the degraded soil. In concrete terms, it's 1.8 centimeters of water, which, as a rule of thumb, is roughly 3 to 4 days of transpiration in a healthy maize canopy, or if you imagine these soils helping a crop get through a longer drought period, it might enable a stressed condition for a longer amount of time. So what do these changes actually do to the yields? First, improving infiltration did improve yields, and I'm going to walk you through these charts because you'll see 3 slides that look very similar. So to isolate infiltration, I kept the soil constant. So these are all with the stabilized soil, which is right in the middle, and I'm varying the curve number from 88 to 68. So as you go from 88 to 68, the mean yield across all 36 years increased by about 6%. And interestingly, there's no responsiveness to the precipitation conditions during that season in terms of the effect of infiltration. Not a significant response of the importance of infiltration to precipitation. And you do see some higher responsiveness maybe towards around the 500 millimeter range, but in general it's not a significant relationship. So this means that infiltration is important whether you're in a drier year or a wetter year. And you can imagine the difference that I illustrated with the curve number chart mattering regardless. In those wetter years, you probably have more large rain events that would just turn into runoff with a low curve number, or a very high curve number, I mean. So that's infiltration. For storage, you're going to see very similar looking charts. Here I maintain the curve number constant, and I vary the soil. So I'm comparing a stabilized and degraded soil with a moderate curve number. And overall, it's a 4% increase in yield for improved storage. So that's a little bit lower than what we saw for infiltration. But interestingly here, we do see a response to growing season precipitation. And this is the easiest way to look at it. If you look at a drought index, it's a more robust, statistically robust response. But this, I think, illustrates that storage is more important in those dry years where there's just so little precipitation. Any amount more that you're able to store is really beneficial. So first set of conclusions, infiltration is more important than storage on average for yields, and infiltration is equally important across all moisture conditions. But when we're thinking specifically about drought adaptation, the storage does come out to be pretty important. Now, when you put these two together, we see an even more substantial yield benefit. Here I'm comparing all the way from a degraded soil with a high curve number to a degraded soil with a low curve number, and overall it's a 12% yield increase across those 36 years on average from improving both infiltration and storage. However, again, similar to infiltration, there's not a response to growing season precipitation levels as far as the effect of both of these together. So to sum it up, I would say that these soil building practices may be a viable option for adapting cropping systems to drought. However, with the caveat that these modeled results are highly dependent on the soil organic matter plant available water relationship in the petatransfer function that's used. Remember, these might be kind of the upper bound. As far as our understanding of soil physics and soil water availability, on the other hand, I haven't addressed any of the chemical or biological effects of including cover crops and other soil building practices in your soil management, and so there may be additional benefits coming out of those areas of soil health that haven't been addressed here. Thank you.
Thank you, Mitch. We got 3 minutes, so we'll take a couple of questions if you have any questions.
Yeah.
I realize it was mostly a model scenario, but we have a lot of growers in our area that just have fallow. And maybe part of the rationale that would be helpful on a spot perspective is to what degree does rooting, with some sort of a cover crop, some sort of other vegetation, help with infiltration or storage short term?
Right. Yeah,
We've got some cover. Does that directly impact infiltration and storage?
So the question was, does rooting on a short-term basis actually give you a quick hit in terms of improving infiltration or storage? I think the quickest response that you'll see is from infiltration. You can imagine presence or absence of a biopore. That's going to make a big difference, and that can happen in the course of a season because of either cover crop rooting or because of reducing disturbance and allowing the biopores that are there to remain. So as far as farmers thinking about how much does improving my soil matter for drought, I think the early story is improving infiltration, and improving storage is a longer term proposition. I don't know that you can improve storage very much, very rapidly. Yeah, I don't have evidence that you can. Do you?
If I can follow up on that, I think a lot of people are saying a lot of the benefit for soil building is 3 to 8 years down the road. So I'm trying to follow with some immediate things that farmers can latch onto.
Mm-hmm.
If we get a 3-inch rain event here in sandy soil, will having that cover crop help infiltrate it faster? And could I time them? Give them a direct measurement and say, your neighbor's not doing anything. Look at how long he had water cooling.
Absolutely, I think that's a great way to do it. So I think infiltration can increase rapidly, and it's also very visual, so could be a good teaching opportunity.
But to use your numbers, but you go on, if the infiltration includes a 6% bump in yield,
mm-hmm.
they might not necessarily see, oh, that puddling is bad, but if otherwise the storage and infiltration have positive benefits for their yield,
mm-hmm.
that's got to sink in.
Yes, absolutely. Yep. Any other questions? Yes.
You use the process-based model, and how you approach the calibration models, and the input parameter, what is the critical parameter for your model?
Right. So the question is about what's the critical parameter for the use of these models, and of course you need to have reasonable crop descriptions so that the yields are in some way related to reality, and the crop descriptions that I used are minor modifications on well-calibrated, well-validated descriptions that I've just kind of tweaked to make sure that they were aligning with conditions in Lancaster County. So I think on the crop side, I feel fairly firm about that, and then I think the biggest parameter that matters is the responsiveness of plant available water to soil organic matter, and that I'm being very open that I think it's an open question what that response is, and it's difficult to measure, and there's a wide range of potential relationships. So I'm going to be going on with this work to explore some of those other relationships and test out different petatransfer functions in this model. I don't know that you can say what the right petatransfer function is. There's debate, but making sure I'm using one that's very representative, I think, will be important.
Well, we're out of time
All
for the
right.
question and answer session, but if you have any question with Hunter, you can meet him later on. So we'll start our next talk.
Thank you.